computer first. Okay. So I will introduce the defense. So good morning, everyone. Good afternoon, Sebastian and Diego, I think. I'd like to welcome everyone to the Master Defense number 1341 of the Department of Computer Science of the Federal University of Minas Gerais. Today, Luigi will talk about the work that he did in the last 2 years. This research belongs into the domain of compilers and programming languages. And the opportunity, I thank the members of the program committee, who are Sebastian Heck from Saarland University in Germany, Diego Aranha from Aarhus in Denmark, and Mario Vin, my colleague from UFMG. So after Luigi gives his talk, the members of the committee will have the chance to ask him questions. And after that, if the audience wants, the attendants can ask questions as well. And then after all that, the committee, including myself, will deliberate the outcome of the defense in a private virtual room. So I will send you guys a link so that you can chat in Google Meet. So that will be after the defense. Okay, so Luigi, you can start whenever you want.
Okay. So let me share my screen. And are you guys seeing?
Yes, all fine.
Okay, so let's start. So this project is about the static elimination of side channels. So first, I'm going to briefly talk about what are side channels, and then about our contributions and our solution, which involves linearizing branches that depend on sensitive information, or as we call them, tainted branches. We also need to compute the predicates that control the execution of each instruction, so that we can repair programs that had their control flow modified due to partial control flow linearization. And finally, I'm going to talk about the experiments that we performed and conclude the presentation. So side channels can be viewed as outputs of a computer system that are usually unintentional and that can be used by an adversary to obtain sensitive information that should not be available to her. So for instance, suppose we have a system that takes X as input and outputs Y. This system, in addition to Y, the system have other secondary outputs like the time it takes to run, power consumption, and etc. And these are what we call as side channels. These informations can be used by an adversary to extract sensitive information. And in this project, we shall focus on the time-based side channels. So we want programs to satisfy a few properties in order to be protected against attacks using side channels. The first is that the sequence of instructions must be the same regardless of the secret inputs. And similarly, the sequence of memory access must be independent on sensitive information. So for instance, suppose we have a system that compares a user's guess with a secret password. The system could be implemented by comparing each element of the arrays GMPW, the guess and password. And once we find an element that is different, which means that the guess is incorrect, we can immediately return 0 or false. That is, we immediately reject the user's guess. This implementation is neither operation nor data invariant, because the sequence of instructions and memory access depend on the value of the password, which is secret. So if an adversary can time the execution of this program, or better yet, she can observe the sequence of instructions and the memory access, she would be able to identify which element was incorrect, which position was incorrect, and with that information, she would be able to, at some point, determine the secret password. The second version of this comparison system is both operation and data invariant. However, it does not behave exactly like the first, because it might have out-of-bounds access that could never occur in the first code. For instance, if we call this function with GNPW with only one element and n equals 2, and the guess is incorrect, so G and W are different. In the second code, we would have access to arrays G and W at index 1, which is out of bounds. But in the first code, this access would never occur due to the early return inside the loop. And we don't want this kind of transformation, because we would be eliminating the side channel. but we would also be introducing another kind of vulnerability, which could be used, could be exploited in other ways by an adversary. So we call transformations that do not introduce out-of-bounds access as memory-safe transformations, which is not the case, for instance, of the transformation proposed by Wu et al. In 2018. And still in contrast to the work of Wu et al., our approach can handle general unbounded loops. And in comparison to the work of Borel et al. From 2021, our transformation is fully static. And finally, in contrast to FACT, which is a domain-specific language introduced by colleague et al. In 2019, we can transform programs written in general-purpose language like C. So we implemented our prototype in LLVM. We published a paper in 2021 with an initial version of this transformation, but this initial version could only deal with loop-free programs. And since then, we have been working on an extension of this transformation to handle general loops, which resulted in a second paper that we submitted for publication this year. So to eliminate tainted branches, we shall apply a partial control flow linearization algorithm presented by Mo and Heck in 2018. And this algorithm was first devised in the context of factorization of SIND programs to remove divergent branches. A branch is said divergent whenever its outcome may vary from thread to thread. So for instance, in this piece of code, the first branch controlled by the comparison I less than n is uniform, is not divergent, because all threads will take the same path regardless of the in every iteration of the loop. But the second branch inside the loop is divergent because the comparison depends on the thread ID. So the path taken by each thread may vary. In our context, instead of divergent branches, we want to eliminate tainted branches, branches that somehow depend on sensitive information. And to determine whether a branch is tainted or not, we shall rely on the notion of control and data dependence. We say that variable y is data dependent on x if y is assigned in an instruction that uses x. And similarly, we say that x is control dependent on p if the definition of x depends on the outcome of a branch that is controlled by p. And the backward slice of a variable x is the transitive closure of its control and data dependence. So we say that a variable is tainted if its backward slice contains a secret, a sensitive value. And consequently, a branch is tainted if it is controlled by a predicate that is tainted. We want that the linearized program to be correct. So in other words, we want PL, the linearized program, to have the same observable effects as the original program P. However, when we linearize a program, we are modifying its control flow graph. So we need to transform some instructions to ensure the correctness of the modified code. And for that, first we need to compute the conditions that enable the execution of each instruction. So first I'm going to define the notion of block and net conditions. So block condition of a block V determines when that block V executes, and that condition of an edge from U to V determines when that edge is traversed. And BC of V is the disjunction of every edge condition from U to V, and that condition from U to V is the conjunction of the block condition of the predecessor U with the predicate that controls the edge from U to V, if any. So first I'm going to show an example for a loop-free program, which is simpler. So this is the control flow graph of a simplified version of that comparison system, that first code, with n equals 2, so 2 iterations of the loop and the loop unrolled. So this graph is acyclic. And from begin to if 0, the edge condition is true because there is no conditional branch. If 0 ends with a conditional branch, so the edge condition from if 0 to return false is the predicate P0, and to if 1 is P0 negated. And that condition from if 1 to return false is the block condition of if 1, which is P0 negated, and the predicate P1. And finally, the block condition of the last block end is the disjunction of that condition from if 1 to end and from return false to end, which reduces to true because the last block is always executed. For general programs, it is a bit more trickier because we may have instructions that execute multiple times due to loops. So what we do is to introduce a notion of time. And we have two special cases that we need to consider. The first is loop headers. A loop header is the unique entry of a natural loop. So for the first iteration, when I equals 1, now here is the number of the iteration or the mark of time, we consider only the forward edges, the edges that are for outside the loop to the loop header. And in the remaining iterations, we consider only the backward edges from inside the loop to the loop header. And the second case are for tainted loop exits. These tainted exits will not exist in the transformed program because these edges will be eliminated. But we still need to identify through which edge the loop would have exited in the original program. So we know how which instructions should execute after the loop. And what we do informally, in this example, the tainted exiting edge is the edge from body to return false. And what we do informally is we can think of this tainted edge as multiple virtual edges, one for each iteration of the loop. And then to compute the block condition of the exit node, in this case, return false, we just compute the disjunction of the edge conditions of each one of these virtual edges. The first step of the transformation is to apply partial contraflow linearization. And for that, we need a special kind of topological sort that is called compact topological sort. And this ordering must satisfy two constraints. The first is dominant compactness. So given a directed graph with a unity vertex S, we say that U dominates V if every path from S, the root vertex, to V must go through U. And we say that an ordering satisfies dominance compactness if whenever we pick two nodes in this ordering, such that the first dominates the second, the first node also dominates every node in between these two in the ordering. And similarly, we say that an ordering satisfies loop compactness if whenever we pick two nodes in the ordering that belong to loop L, the nodes in between these two also belong to L. And we ensure loop compactness in this work by collapsing loops into single nodes. So let's see an example. This is the contraflow graph that I showed before of the comparison system, and block body is tainted. The first thing that we do, as I said, is to collapse a loop formed by body, latch, and header into a single node. And we consider the loop as tainted, the loop node as tainted, because the loop has at least one exiting block that is tainted. And then we compute the sort for the ordering for this new graph if the loop collapsed. And after that, we kind of open the loop node and we compute the compact sort for the elements of the loop. It's considering the back edge because we need an acyclic graph. And then the compact sort of the original graph is just a merge of these two. In this case, it is begin, header, body, latch, return true, return false, and end. So for tainted loops, the tainted exits, as I said, will not exist in a transformed program. And the public exiting edges, we redirect every public exiting edge to a single exit node, which is the first that comes first in the compact sort. In this case, it is return true. And this is the final partially linearized graph for this example. And notice that the exiting edge from body to return false no longer exists. So the loop formed by body, latch, and header now can only terminate due to public information. The second step of a transformation is to fix phi functions. A phi function is just an special instruction that joins multiple definitions of the same variable. In this example, the basic block body, the basic block B is tainted, and after linearization, B will be linked to D and D to E. So the last block after linearization will have only two predecessors, E and F. And so the incoming value x1 will no longer have any incoming edge that it relates to. So the phi function is now broken. And what we do is simply we replace the old phi function with a new phi function, respecting the new incoming relations. And for the incoming values that cannot fit in the new phi function, we add 67 instructions, which stand for constant time selector to select these incoming values. And we also add other few functions for the incoming value, in this case x1, because in the linearized code, linearized control flow graph, there may be paths that did not exist before linearization, and so x1 may be, in this case x1, may be undefined in these paths. And the third and final step.
Can one of you guys switch off the micro? I think it's Breno.
And the third and final step is to transform loads and stores. In our toy language, the language that we use to design our ideas of transformation, stores are the only operations that can cause observable effects. So first, to transform load stores, we first need the notion of post-dominance, which is kind of similar to dominance. So given a directed graph with a unique exit vertex D, we say that V post-dominates U if every path from U to the exit node D must go through V. And we use post-dominance to determine the influence versions of tainted branches so that we transform every load and store within these versions. So the influence region of a node U is a set of all nodes in paths from U to its post-dominator V, excluding U and V. So for example, in this control flow graph, the influence region of body includes return false because there is a path from body to end, which is the post-dominator of body. That includes return false. And there's also a path from body to end that includes latch, header, and return true. And finally, body itself is in its influence region because it is part of a loop formed by body, latch, and header. So this is the only case when the node itself is part of its influence region. So here's an example of the transformation of a load and store. So first the load. The first thing that we do is that we try to determine if the access is safe, if it is in bounds. So for that, we need to somehow try to infer the size of the array. We need that information. And then we use the block condition of the basic block, in this case, the block body, to determine if the access should execute or not, or if the access would execute in the original program. And then if the block condition is true, that is the access the load should be executed, or if we know that the load is safe, the access is safe, we perform the original load. Otherwise, we replace this load with a load to a shadow memory with some dummy value. For stores, the first thing that we do is to create a safe load, which in this case, I'm just assuming is the piece of code from figure B. So the loaded value would be pw.i. So that we can get the current value stored under that address, or depending on the circumstances, under the shadow region. And then we use the block condition to select between, in this case, x, the value that should be stored, or pw.i, the current value stored under that address. So if the block condition is true, which means that the store should be executed, it is executed, the value is updated. Otherwise, the store is silent. Our transformation delivers a few properties. The first one is that loops can only terminate due to public information. The second is that the transformation is memory safe. That is, we do not introduce out of bounds access, as I said before in the beginning of the presentation. And the third is that partial control flow linearization alone ensures operation invariance. And for a specific class of programs called public safe programs, partial control flow linearization also suffices to ensure data invariance. So we say that a program is public safe if for every memory access at an index I, this index I is not dependent in any way on a secret. And in addition, for every access that is contra-dependent on a secret, we can prove that the access is in bounds. This definition comes from the paper of colleague et al., which introduced the fact, the domain-specific language. And in the case of fact, all programs written in fact are by default public safe. So in our case, for public safe programs, we deliver the same properties, the same guarantees delivered by fact. And the last property is that the code produced by our transformation refines the original code, in the sense that the code that we produce never leaks more than the original code. That is, we never produce a code that is worse than the original version. And we performed a few experiments to try to answer 3 research questions. The first one is, by how much does the proposed approach increases code size? The second is, what is the running time of applying a transformation? And the third is, by how much does the proposed approach impact the running time of programs? And we used self-agreement to assert that the instructions executed by each benchmark do not vary for different secret inputs. And we instrumented the benchmarks to check for the sequence of memory access, and for shadow-safe programs, either they are data invariant, which is the best scenario, or some memory access were replaced by access to the shadow region. So we performed the experiments on top of 21 benchmarks, which were also used by Wu et al., the work for 2018. And here I'm showing the number of LLM instructions in each benchmark. And at the top of the chart, the numbers for the original programs. So Leaf plus PCFL is our general approach that uses small and hex partial control linearization. And Leaf without PCFL is the first version that I've implemented that can only deal with loop-free programs. And Leaf without PCFL yields much more instructions than Leaf plus PCFL, which is expected because Leaf requires loops to be enrolled, so there will be more instructions by default. SC Eliminator, which is the prototype from Wu et al., also suffers from the same problem, that loops need to be unrolled, and it yields much more instructions than Leaf. And Constantine still yields, it performs better than the 2 approaches, but it still yields more instructions than Leaf plus PCFL. But it's important to point out that Constantine does more than Leaf. In our case, in our project, we are only applying control flow linearization. Constantine, on the other hand, in addition to control flow linearization, also applies what they call as data flow linearization, whose goal is to try to close cache or memory-based side channels. Nevertheless, there is an important difference between our control flow linearization and Constantine's, which is that Constantine's control flow linearization requires one-time information. Constantine is a mix of a static and a dynamic transformation. And the second chart shows the time taken to apply the prototypes, transformations, in milliseconds. And I'm also showing the -03 optimization pipeline as a baseline, just for sake of comparison. And Leaf without PCFL takes a bit more time than Leaf plus PCFL, but again, this is expected because loops are unrolled, so there are more instructions to be transformed. SC Eliminator, again, suffers from the same problem, so it takes much more time than Leaf. And Constantine also takes much more time than Leaf plus PCFL. But for Constantine, we are not sure if the numbers are accurate. I'm just showing them for sake of comparison, but we are not sure how to properly measure the time taken by Constantine, because Leaf is just an LLM based tool. SC Eliminator is just an LLM pass, so it is easy to measure the time taken by these tools. But Constantine, the build script for Constantine is much more complex. It has multiple calls to the LLVM optimizer, and we are not sure what exactly we should measure or not. So this third chart is about the time taken to run the benchmark. So the overhead that the tools add onto benchmarks in microseconds. And leaf with or without PCFL behaves pretty much the same way. Eliminator adds a bit more of overhead onto programs, and Constantine, for a few benchmarks, it performs better than Leaf plus PCFL, but for the majority of the benchmarks, it performs worse. And for a few specific benchmarks like Lucky and Twofish, it performs much worse. And so to conclude, we showed how to apply Mo and Hex partial control flow linearization in the context of software security. We showed that partial control flow linearization is enough to ensure operation invariance, and that for public safe programs, it also delivers data invariance. Our transformation is fully static, and it handles general programs with unbounded loops. And as I said before, we are only applying control flow linearization. So we cannot protect programs against all kinds of against cache-based attacks. So as an example of a future work that may be worth pursuing, we could, for instance, try to combine our control flow linearization with Constantine's data flow linearization to try to deliver full protection against for a larger class of programs. And in this case, we would need to compare our control flow linearization using Mo and Hex partial control flow linearization with Constantine's default control flow linearization, which uses runtime information. And so here are the main references that I use in this presentation. And that's it. Thanks for watching, for hearing.